Alright, my name is Hayden Harris. Welcome to my physiology channel. And on this channel, we believe in guns, America, and physiology. Alright, so first I'd like to talk about homeostasis. To put it extremely simply, homeostasis is your body's desire not to be weird. Physiologically, we like to be at a comfortable point in all sorts of different definitions. The easiest way to think about that is, let's start with temperature. So we all know that the typical temperature for a body is about 98.6 degrees Fahrenheit. The homeostasis is actually, really it's kind of a range that exists in there, and that 98.6 is what we call a set point, meaning it's an individual point on our graph. If I was to go over here, and let's say this represents 98.6. This is my set point right here. The reality is, I do this in between all day long. So you might take my temperature one day or 1 minute and I'll be at 99, and 5 minutes later I might be at 96. But the point being is our body maintains a homeostasis in that range. To do this, it has pathways. Reflex pathways is like what we like to call them in good old physiology. But we have two types of neurons we're concerned about here. We have an efferent neuron and an afferent neuron, E and an A. So when we're taking in signals, perfect example being, I touch something hot and I go, ouch, that hurt. That initial pain I feel, what's gonna happen is I'm gonna have a signal sent up my hand, through my spinal column, up to my brain. That's an example of an afferent neuron. An efferent would be the example of, I don't know, let's say I'm too hot and I need to start sweating to cool down. The efferent, with the E, is going to send that signal from my brain to all my sweat glands all over my body and say, hey man, it's time to cool down. I'm going to start sweating. So in order to, what these pathways do is they're actually going to be regulating your temperature, but how does your body know what to do when? Like what's actually, I guess a better question would be, what's actually happening inside your body when you're too hot or you're too cold? So there's two types of feedback systems. Feedback system is just meaning that it's what our body does in these scenarios where we're on the verge of going out of homeostasis, which is again that comfortable range we like to exist in. The two types of feedback systems we like to talk about are negative feedback and positive feedback. Now you need to pay close attention here because this can be a little bit confusing. It's kind of counterintuitive. So a negative feedback, I'm going to put feedback loop. Negative feedback loop. What that means is this is usually the good thing in the body because it means we're trying to return to set point. Going off of this chart I had drawn earlier, I'll draw a little bit larger so we can see what we're talking about. Say this is my set point again, and I start cooling off because I started sweating. But all of a sudden, my body is on the verge of going out of homeostasis. That's bad. We don't want to do that. So naturally, my body is going to have a response to the afferent and the efferent systems and tell my body, hey, stop sweating, we need to heat up. So the negative feedback would be reducing the effect, and I'm going to try to warm back up. That's a good thing, because we want to be in homeostasis. Now there's another type of feedback system called positive. Now I'm going to explain positive first, in terms of the way it's bad. But I don't want you to think positive is always bad, because it can be good. So in terms of where positive is bad, to stay on our train of thought here, if I'm sweating and I'm cooling down, but for some reason, something happens somewhere that I just can't stop sweating, and I'm gonna go into hypothermia, my body, meaning it's out of that temperature homeostasis, it's gonna start going down and down and down, and I'm going to continue to go away from the set point, away from homeostasis. Not a good thing. Now this specific type of positive feedback is actually called inadequate negative feedback. A little confusing, but and I'll explain that a little bit more, inadequate negative feedback loop. The reason why we consider this a type of positive feedback loop is because essentially my body is doing a negative feedback loop and it's trying to fix it, it's trying to fix it, it's trying to fix it, and is it going to keep doing a negative feedback in order to fix this problem, when in reality it's just making it worse. So this doesn't work as well for temperature, but what we can talk about is what would happen is if you or someone that you don't like was bleeding out on the ground. What's happening? They're bleeding, they're losing blood volume, and they're dying slowly. What's their body gonna try to do? Well, when you lose that blood volume, the initial thing that you have, or the initial stimulus, if you will, is the loss of blood pressure. Your body wants to return your blood pressure back to homeostasis, so it's going to, the stimulus would be the loss of blood, and then it's going to that's going to send a system through, or send a signal through your control system, or your control center, and it's going to try to increase your blood pressure via increasing your heart rate and your peripheral resistance. So what if though the hole or the wound was large enough that by increasing the heart rate, it's actually going to cause me to lose more blood. But as I lose more blood, I'm going to try to increase my heart rate and increase peripheral resistance, but that causes me to lose more blood. It's a positive feedback of a bunch of negative feedbacks. Not a good thing. We don't like that. So that's an example where positive feedback is bad. Now we do have traditional positive feedback, which is a good thing, and we see these we see this a lot with, a woman in labor, for example. Oxytocin is a hormone that's released from the limbic system in your brain. And when a woman's going into labor, in order to contract, they have to release that oxytocin. The oxytocin tells the uterus, hey, you should contract. And the contractions tell the body to release more oxytocin. So one thing causes an external propagation of another thing. Exactly what we saw with this inadequate negative feedback, but in this case, we're talking about a good version of positive feedback. All right, now that you're an expert in all things homeostasis, we're going to move on to a slightly different subject called protein transport. So there's a couple, what this means is we have molecules on the outside of something, usually a cell, and we need to be able to get those molecules from the outside to the inside. Now specifically, when we have stuff on the outside of our cell, let's say this is our cell, and then this is the other stuff. We usually refer to this as the extracellular environment, and then we call this the intracellular environment, but for these purposes, I'll just call it cell. So when we have stuff outside of our cell that is charged, or it is large, or it's polar, aka it's water soluble, they cannot cross the cell via simple diffusion. They have to have help from a friend, just like we all need help from friends sometimes to accomplish things. Atoms and molecules are no different. That being said, there's two types of facilitated diffusion. That's the word for this. That's the word that meaning we're using proteins to help our molecules across that plasma membrane of a cell. So in facilitated diffusion, we have a bunch of different protein channels that help us accomplish this. There is something called a ligand-gated protein channel, and this just means that it requires something to come and attach to it, such as an external stimulus, in order for it to open up and for it to be, or for the molecule to be able to go through the channel. We also have something called voltage-gated, and this means we're waiting for the right difference in electrical gradient across our cell in order for a channel to open up. This is super, super common in muscles. That's how I'm even talking to you right now. Thank you, voltage-gated channels. And then we have the mechanical channels. Mechanical gated, I guess. Mechanical gated channels just means they're waiting for some sort of physical stimulus that can take all sorts of different forms. But once that physical stimulus opens up, the lid pops open, and whatever molecule we're trying to get through is going to flow right into our cell. That's super cool. Now we're going to talk about the other form that we see as far as protein and protein transports go is active transport. Again, we have subcategories of active transport. We have primary and secondary. But first of all, what is active transport? Well, I'm here to tell you today. Active transport is when we're causing things to go against their concentration gradient. So that is a key point I forgot to emphasize earlier, is that in these facilitated diffusions with all these protein channels, it's usually something going with, not usually, it's always something going with the concentration gradient, meaning that there's more stuff on the outside than there's inside, and due to osmotic pressures, they want to go inside the cell. With active transport, we're doing the exact opposite. We might have some more stuff on the inside and less stuff on the outside, or maybe there's just no concentration gradient, but we are going to use energy in order to get stuff to go against a concentration gradient. We also use this to create concentration gradients, which we'll talk about here in a minute. So the most common example of active transport, this is going to be our primary active transport. Primary active transport. We have something called a sodium potassium ATP ACE. So ATP is the central unit of energy inside cells. It's sort of like their currency, their dollar. It's how anything occurs. It's how we get anything to happen, or the vast majority of things that happen in our body, or something like ATP. These primary active transport pumps specifically, they have, in the simplified version, they require to input 3 Na pluses, and then once they have that, they're going to kick that out of the cell. And then we're going to input 2 sodiums. And that's going to go into the cell. That's pretty cool. And it's going to create this concentration gradient via ATP. Long story short, we have ATP stands for adenine triphosphate, and we're going to take one of those phosphate groups, we're going to bust that bond, and in the process we're going to use an antiport, which is when we take 2 things and we're going to force them across a membrane. I'm going to have to cut that part out because that's not what antiports are. But you can just keep on recording. I'll fix it later. When we have, let's see. Yeah, so when we have our sodiums and our potassiums loaded up, we're going to have ATP, and it's going to come bust one of those bonds, or bust one of its phosphoruses off, and it's going to push them across the membrane, and we're going to create an electrogradient difference. Our other type, we have secondary active transport. So this one can be a little bit misleading, because secondary active transport does not actually use any ATP. Rather, it's bumming off the ATP consumed during primary active transport. Our bodies are pretty smart that way. They know how to be lazy. So what they're going to do is, like I said, we're going to create a concentration gradient. The example I gave is sodium and potassium. But secondary active transport is going to rely upon that concentration gradient previously established by primary active transport, and it's going to pair things that have, or pair things that want to go across the gradient with things that do not want to go across the gradient. So let's say, for example, on the outside of my cell, I have a bunch of sodium. And on the inside of my cell, I have a bunch of calcium. If I want my calcium to leave, even though it doesn't want to leave, let's say there's even more calcium on the outside of my cell. So just as a note, the natural concentration gradient of calcium is it wants to go in because there's more out here than there is in here. The natural concentration of sodium is, again, it wants to go in because there's more out here than there is in here. So it can do something where it pairs sodium with an internal calcium, and sodium's going to go in, and calcium's going to go out via secondary active transport. When we're taking 2 things and we're moving them in opposite directions, that's called antiport. Pretty easy to remember, because anti, opposite, equals opposite direction. And The other version of this is the exact opposite, we call a symport. Sim, kind of together. Symport is when we have two things, we're pairing two things, and we're moving them in the same direction. Again, one has a concentration gradient that it likes, the other one does not, but they're paired together in a symport, so it works. Again, these are just two types of protein membranes. All right, now I'd like to bring you over to this side of the board where we have some definitions we would like to get out of the way. So with each of these, I will either just give you the definition or I'll draw a cool little picture. We'll see what happens. So we'll start with specificity. Specificity refers to our channel proteins. So let's say we have a channel protein for, I don't know, sodium, right? Let's say this channel protein, that's this dude, and we have sodium. So we call him a sodium channel protein because he only lets sodium through. Imagine I had potassium. Now, bear in mind, potassium is in the same periodic column. It's also an alkaline earth metal. So it has the exact same characteristics, except it's a little bit bigger. This channel will not let potassium through, even though they're very similar. The reason for this is the specificity of the pump. So we write Na+, but really what's actually happening is, if I were to draw it over on the side here, we have Na+, and then we have a bunch of water molecules in solution that sort of make this shell around it. And that just essentially means that, or this is what creates specificity, is when sodium goes to enter, there's a bunch of other little proteins in here that allow the sodium molecule to get through because they interact with the water just so precisely. And same thing applies for potassium. Potassium has a different hydraulic shell of water around it that designates its specificity. On to rate. Rate has, I broke this into two different categories. There's simple rate and simple diffusion rate and facilitated diffusion rate. Rate in general is just what it sounds like, but in terms of our cell over here, it's how fast stuff is getting across the membrane. So for simple diffusion, there's actually a really nice equation given us to our favorite guy, Fick. Fick came up with an equation that says J, which is equal to our speed of diffusion across the membrane, is equal to negative D, which is a coefficient, times our surface area of the cell, divided by the change in C and the change in X. So what this is, or I guess the big thing here is delta X is the difference in, or the thickness of the membrane. So really what this is saying is that, hey, to get stuff across the membrane on a simple diffusion level, it's going, the thicker the membrane, the longer it's going to take, but it's usually longer by a proponent of 10, or to the 10th power. So if the difference between going across like 1 centimeter versus 10 centimeters isn't just 10 more seconds, it's like, I don't know, 10 to the 10th or somewhere in that range. Point being is it's much harder to get across thicker things. Thank you, Fick. Our rate in terms of facilitated transport, well, that's actually kind of limited by the protein channels or pumps themselves. If it's super efficient, then it's going to go faster. You could also have a problem with, like, if you don't have enough pumps and you're under saturation, which we'll get to there in a second, meaning you have too many molecules, your rate is going to be limited by the number of pumps you have, or channels. Energy source, we briefly mentioned this, but the primary source of energy in all cells is this molecule called adenine triphosphate. Why is it called that? Because we have nitrogenous-based adenine with literally 3 phosphate groups. We also see other variations such as GTP. I think there's even something called AMP. Regardless, energy sources come from busting bonds inside these molecules. We typically refer to the molecule itself as energy. On to direction. So some pumps, like our antiports and our symports, have directionality. That's just determined by their configuration and their way they're made up. But point being is, if I have an antiport for sodium and potassium, it pumps sodium out and it pumps potassium in, it's never going to do the reverse. It's never going to pump sodium in and potassium out. It has directionality. Saturation is when it's in terms of how much of our how much molecule do we have compared to our pumps. So when we're overly saturated, what happens is it's like Imagine 100 people in a small room, and there's only like 1 or 2 doorways. Their rate is limited by the number of people that can get out the door at one time. But now imagine we had 100 people with 1,000 doors. Well, the rate is just going to be determined on how fast those guys can get through the doorway. Exact same thing here. Saturation is if we have too many of our molecules and not enough, or too many of our molecules and not enough channels, then we're not going to, our rate is, or that's when saturation occurs because we can't get our stuff through the cell fast enough. Competition is when we have molecules that specifically bind to our channel proteins and blocks our sodium or our potassium from getting through. This is a regulatory mechanism our body uses to control some of the processes going on in our body.